Assalamualaikum and hi everyone. Welcome back to my another e-lecture. Before that, if you haven't subscribed to my YouTube channel yet, please do so, and a big thanks to those who already have. Inshallah, you will see more helpful videos from me popping out in your YouTube feed. Before that, in lecture 4, we went over the very basics, including an introduction to digital images and resolutions. We also talked about pixels and color imagings. This time, it is for our Geospatial and Remote Sensing course, lecture 5, week 5. Today, we will go deeper into two parts. Part number 1, multispectral sensors, and part 2, digital image processing or pre-processing, which is the key topic for this course. In today's class, we will focus on two final course learning outcomes, CLO2 and also CLO3. CLO2 is to develop the ability to collect, handle, and use digital spatial data for mapping, analysis, and also modeling, while CLO3 is to evaluate the source, nature, and quality of the spatial data. For this lecture, we will be covering two main topics, which are part 1, multispectral sensor, and part 2, digital image pre-processing. But for this video, we will focus more on the part 1, which is the multispectral sensor. Before we go in detail into multispectral sensor or scanner, let us understand the sensor used in remote sensing. This diagram shows a classification of sensor based on two key types, passive and also active. Each of these types is further broken down into various categories depending on their functions, whether they are scannings or non-scannings, imagings or non-imagings, and what specific technology that they utilize. Let's go through each section in details. So we go with the passive sensor first. So this sensor detects natural radiations that is emitted or reflected by the object or surrounding area. So they don't emit any energy themselves, but capture energy that is naturally available. Non-scannings, we go with non-scanning first, so it has in non-imaging and imaging. So for the non-imaging, these sensors are designed to capture non-image data. For example, it has microwave radiometer that detects microwave naturally emitted by objects, magnetic sensor measures magnetic field strength, gravity or gravimeter measure gravitational force of the earth, and also Fourier spectrometer is to analyze the spectral compositions of incoming light, primarily used for atmospheric studies. And so we also have other applications for the non-imaging sensor. And then we'll take a look on the imagings. So this sensor capture image data typically like photo. We have a camera and of course taking image for various spectral bands. We have monochromes capture black and white images. We have natural colors capture images in the visible color spectrums. And we also have infrared capture images using infrared wavelengths. And then we have color infrared capture images in both visible and also infrared wavelengths. Others camera that might use different sensor or bands. And then we also have the scanning for passive, which is only for the imaging, meaning that is only can take a photo. So these sensors scan the scenes and create images based on the scan. So we have image plane scanning. So this system scan an image directly on the image plane. For example, TV cameras, a traditional video camera, and solid scanner, a device that scan using solid states sensor like CCD or CMOS. And then we also have object plane scanning, which is the scans the objects plane using by moving the sensor or using scanning mechanisms. So we have optical mechanical scanner that use rotating mirror or other mechanical devices to scan across the object. So this one will be covered on these topics. And then we also have microwave radiometer. Is to operate in the microwave band to scan the scenes to build an image. Next, we have active sensor. So active sensor emits their own energy and measure the return signals reflect back from the objects. These are very useful in conditions where natural energy is insufficient, such as in low light or during night time. So we have non-scanning and also scanning. We take a look on the non-scanning first. Non-scanning, we have the non-imaging, which is not a capture photo. So this active sensor emit energy but not designed to create images. For example, it has micro radiometers that we are like what we discussed in the non-imaging over here. We also have microwave altimeter, measure altitude by calculating the time it takes for the microwave pulse to return. And then we have laser water depth meter to measure the depth or water depth using a laser pulse. And then we have laser distance meter, measure the distance to an object using a laser pulse. And then we have scanning, which is generate an image or imaging. Other plane scannings, we have real aperture radar, use radio wave to detect and map the surface. And then we have synthetic aperture radar, SAR, a more advanced from a radar that create a high resolution images by combining multiple radar data points. And then we also have image plane scannings. So this is kind of passive phases array radar, use multiple radar antennas to detect and create images from the reflected radar signals. So these are basically the different type of sensor, but the main things or the main key here, it has passive and also active. Passive, it uses the natural reflections of the objects, while active, we generate and the objects will receive the signals and then we process the data. Now we're going to look into the passive sensor first. So passive sensor in general is detecting natural available energy, either reflected by sunlight or visible wavelengths, or emitted energy, which is thermal infrared. So this sensor can only capture reflected in energy where the sun is shining on the earth, meaning no reflected data can be collected at night. However, emitted energy such as thermal infrared can be detected both days and night, provided there is enough energy for the sensor to be recorded. Now we take a look on one of example of passive sensor, which is multispectral imagery. Multispectral imagery is a type of remote sensing data that captures information across multiple wavelengths of the electromagnetic spectrum that we have covered in the previous lecture. This means that instead of a single image, we get series of images, each representing a different part of the spectrum. So these images can be used to identify and analyze various features on the Earth's surface, such as vegetation, water bodies, and urban areas. And then we need to understand about the terms color composites. So this one will be covered in our lab, but I'm going to talk in general about the color composites involved in the passive sensor. Color composites in general are created by combining 3 or more spectral bands from a multispectral images into a single color image. This allows us to visualize the data in the way that is more likely or easily to interpret by ourselves. For example, here we have 7 bands of multispectral image, and we can manipulate them by combining and assigning color to create a desired image. Most software provides an RGB red, green, blue combining function like this. If the correct band are assigned to the corresponding RGB channels, it will result image what we so-called as true color composites. In this case, the red band, which is the band 3, is assigned to red. Okay, red band, band 3 is assigned to red, and the green band is assigned to green, which is the band 2. And then the blue band is to blue image or the blue channels, which is the band 1. So 3, 2, 1 is red, green, and blue channels. So when we assign to a correct channels or correct color, it will produce an image similar to what you see on the Google Map in satellite mode, like this one. 3 to 1 RGB. We assign the same color in the correct channels. So, however, what if you assign different color bands to the RGB channels? Okay, for example here we will get what we so call false color composite channel, or false color composite, sorry. So different FCC images are used to different purposes as shown in the image on this. Okay, for examples, we assign 432 band 432, which is not a correct color or spectrum wavelengths, into different channels. I mean blue channels. We assign band 4 into blue channels, band 3 into green channels, band 2 to red channels. So it's not a totally correct channels, and it will produce some things like this. And if you use different spectrum into different channels, you will also get different color of image. So these are an examples of false color composite. So the image illustrated here is a basic setup of a multispectral sensor system. We're going to talk about this sensor acquisitions later on, or scanners acquisitions later on. But I'm going to talk about the key components that we have when we conduct the color composites. We have detectors to capture electromagnetic radiation from different spectral bands, each sensitive to a specific wavelength range, like what we discussed in electromagnetic spectrums. And then we also have lens and filtrations. The lens focuses the radiations onto the detectors, and the filters ensure only the desired wavelength reach all the detectors. And then we have the spectral bands here. So the system shows 4 bands: near infrared, NIR, red, green, and blue spectrum, representing different part of electromagnetic spectrum. And how it works: number 1, radiations collection. So the lens gathers electromagnetic radiation from the scenes, and then the wavelength separations. The filtration system divides the incoming radiations into specific spectral band. And then number 3 is detections. Each detector measures the intensity of the radiation within its representative or respective band. And then lastly, we have the data recordings. The measured signals are recorded and processed to form a multispectral image. The image here shows an infrared false color composite which is created. And it is a technique used to emphasize certain features in an image that aren't easily seen or observed in true color composite or natural color. To explain the process, first we need to capture multispectral data, like what I have explained here, from a multispectral bands, including near infrared, NIR, red, and also green. Then we assign color to each band. So NIR is assigned to red, the red band is assigned to green, and the green band is assigned to blue. So it's not correct channels. After assigning this color, we combine the channels to generate the false color composites, like what you have seen here. In this image, here we can see that the individual grayscale image represents the NIR, red and green channels. So the color wheels demonstrate how these 3 primary colors, red, green, and blue, can be combined to produce different colors. So the final infrared false color composite image shows the result of combining those color assigned bands. Now looking at the key features of an infrared false color composites. Here, vegetations appear bright red or green because healthy plants reflect a lot of NIR radiations, while water bodies over here and over here, we can see often appear dark blue or black, since they absorb most NIR radiations. And for the urban area, in this area, usually shows up as gray or white because they reflect evenly across several wavelengths. So these are several benefits to using these composites. It allows for better features discriminations highlighting details like vegetation health, water bodies, and urban structures that are harder to see in the natural color images. It's especially useful for vegetation analysis, helping us monitor plant growth, stress, and land cover changes. And that is also valuable for water resource management, allowing us to identify and assess the water bodies and probably their quality. And for urban planning, it provides insights into land use, urban growth, and infrastructure. In short, infrared false color composites provide a wealth of information about the earth surfaces that we wouldn't able to capture or detect in regular natural color images. So this make them a powerful tools for scientists and researchers alike to study further. Okay, now we move into active sensor. So active sensor provide their own energy or own energy source to illuminate targets. So they emit radiation that is reflected back to the sensor, allowing for measurement regardless of times or day or seasons that passive are unable to do so. So active sensor can assess wavelengths not provided by the sun and offer better controls over illuminations. However, they require a significant amount of energy. So a common example of active sensor is a synthetic aperture radar or SAR. So here is an example of active sensor imaging. So the image is a RISAT-1 radar satellite image of the Tripura state in India, captured on September 2012. So it showcases various geological structures, including plunging antiform and seaform. By studying the pattern of these faults, geologists can learn about the history of the regions, tectonic activities, and the formation of its mountains and hills in general. Okay, now we're going to talk about multispectral scanners and devices and how the data from these scanners works. So we're going to talk about multispectral data acquisitions. So as for multispectral data acquisitions, there are two main types of scanning systems utilized by satellite remote sensings or remote sensor to gather multispectral images data. So they are across-track scanning, also known as Wisbroom, for example, Landsat, and also we have a long-track scanning, also known as Pushbroom. For example, we have Spot and also Econos. Here is the image of Wisbrooms and also Pushbrooms that we're going to talk later. Looks on the Wisbroom or across-track scannings. In this system, a single detector with a narrow field of view moves across the satellite track, scanning the terrain line by lines. So a rotating or oscillating mirror directs the detector's fields of view across the scenes. An example of satellites using this method is Landsat satellites. The advantage of these designs include its simplicity, lower data rates, and better radiometric calibrations. However, it does have some drawbacks, such as a slower scanning speed, limited spatial resolutions, and greater susceptibility to atmospheric effects that we're going to discuss later in part 2. So the image here shows the scanning pattern of Wisbroom sensor. And here is the GIF. It shows that how the Wisbroom work is site-to-site cleanings. So this is a technology commonly employed in satellite remote sensings. Here we have the scanning directions, and which is the horizontal path the sensor takes as it scans the terrain, and then there are flying directions, which is indicate the way the satellite is moving forward. Now here, how it works. So as the satellite advances flying directions, the Wisbroom sensor scans the terrains perpendicular to these directions, line by lines. So each line of the image is captured as the satellite progresses forward by one step within arc below the system, typically of some 90 degrees to 120 degrees. So in the image, you can see two rows of squares that represents the ground area being scanned. The blue squares highlight the portions of the grounds that is sensor is imaging at any given moment, while the scanning directions remain perpendicular to the flying direction. So this is how it scans over the times with the help of rotating scan mirror. So that's why you can see it's kind of swiping from side to side until it finish, and then the rotating start again. We're going to go with the row number 2, and the process is repeated with the row number 3, and so on. To push broom or a long track scannings. So in this system, a linear array of detectors captures an entire lines of data simultaneously as satellites move forward, and is similar to a push broom sweeping across a floor like this one. So difference with the whisk brooms from one pixel to one pixel, this one is a long track scannings in one directions. So this method eliminates the needs for moving part. Example of satellites employing this technology, including Spot and Econos that we discussed earlier. So the benefits of long track scanning includes faster scanning speeds, higher spatial resolution, and reduced atmospheric effects. On the downsides, this system has a more complex designs, requires higher data rates, and may experience detector saturations that we're also going to discuss later in the next parts. Here how the push brooms sensor operate as the satellites move forward in the flying directions. So the sensor captures an entire lines of data all at once, and each detector in this sensor arrays corresponds to a specific pixels in the image, allowing for efficient data collections. In the next image, you can see that the 3 rows of squares that represents the ground area being scanned. So the blue square signify the portions of the ground being imaged by the sensor at any given time. Notably, the scanning directions align with the flying directions, which enable the push broom sensor to gather data continuously as the satellites travel. So this is the opposite way of acquisitions. Compared to the whisk broom. Whisk broom is perpendicular, while for the push broom is parallel to the flying directions. Okay, now I can turn on my camera again because we have space over here. So we're going to have a look on the comparisons of multispectral scanners and devices. Here the image shows various types of remote sensing imaging system used to acquire multispectrals and also hyperspectral data that we discussed in the previous lecture. So let's start by looking at the analog frame camera and films. So these traditional systems relies on photographic film that use silver halides crystal to capture images. So light passes through a lens and is focused onto the films and creating an image. So the resulting photograph is a negative, meaning the tones and geometry are reversed. So while this method can capture multiple bands, it is limited by the chemistry of the films, making it less versatile than common digital methods. Okay, we move to digital methods. So we have digital frames camera area arrays. So we are enter the realm of digital imaging. Here, instead of filmings, we use digital detectors arranged in an array to capture the image. So the light passes through the lens and is divided into different spectral bands like infrared and near infrared, NIR, red, green, and blue. So each band has its own set of detector, as shown here, where it captures the data simultaneously at one time. So this is not only improve resolutions but also provides better, what we can say, better spectral fidelity, meaning we get clearer, more detailed images compared to analog films. Next, we have the scanner. So this is a system that uses a scanning mirror like we discussed in the whisk broom, and it has a discrete detectors. So the mirror sweeps across the scene and capture it lines by lines. So the reflected light passes through filter to detector that record the data in separate bands such as NIR, red, green, and blue. So this method allow for a wide ranges, wide coverage, but because it captures the scenes over time, it might introduce some distortions and time lapse effect because the rotating scanning mirror too. And then in terms of push broom and whisk broom linear arrays, we have discussed earlier, and I think we just skip it. And then lastly, we have hyperspectral array, which is the most advanced of the system shown here compared to other scanning system. So this system is designed to capture a much broader range of spectral bands, 100 of them for each pixels. Okay, remember we do the comparison between multispectrals and also hyperspectral. So this is how it is. So light is dispersed into these narrow bands using dispersing elements. So that's why you have multiple spectrals, and this detector captures this detailed spectral informations individually. So hyperspectral imaging is extremely valuable for identifying subtle differences in surface materials and analyzing the environment at a much more granular levels compared to a multispectral system. Okay, so to summarize the part 1, this remote sensing system represents an evolution in technology from analogs to digitals, from frame-based capture to line scanning method, and from multispectrals to hyperspectrals data collections. So each of these advancement increases the precision and the depth of the data, allowing for more detailed analysis of the Earth's surface. And I think here is the end of part 1. Stay tuned for the incoming part 2, which is digital image pre-processing. So we're going to discuss in details on digital image pre-processing before we go into actual processing. Again, don't forget to subscribe to my channels, Discover Geophysics. Thank you and have a nice day ahead.